Hello, this is Truth Socrates. Welcome to our 7th video in my series for multivariable calculus, known as Math 5C at Pasadena City College. So in our last video, we finally finished with my first handout, which was about thinking in 3 dimensions. So today, in this video, we get to start on our main handout, which is integrals in higher dimensions. So in this handout, we talk about several kinds of integrals: double integrals, triple integrals, contour integrals, flux integrals. And so we are going to create these integrals as we go along. And they are more or less patterned after the definite integral that we see in basic calculus. So in this video, we are going to review the meaning and the construction of the definite integral. And we are going to see a different way to look at the definite integral, which has to do with what are called density functions. We are going to also review a couple of techniques, integration techniques, that we will need when we finally get to compute double integrals. Okay, so we will talk about basic U substitution, and we will talk about integration by parts. Those two techniques in particular are going to be very useful when we compute our double integrals. Okay, so let's jump right in. Let's review what is the definite integral. Okay, so we have this definition that we see in basic calculus. You start with a continuous function f of x on a closed interval from a to b. Okay, and the first time you saw this, it probably took you several minutes to create the definite integral. And at the end of that period, you have this equation. Okay, but don't worry, we will go over what this equation means, right? So we write it as the definite integral from a to b of f of x dx is the limit as n goes to infinity of a summation, what we call a Riemann sum, summation I equals 1 to n of f of x I star delta x. So let's review what these symbols mean. All right, so the first symbol that we see is n, and n is going to go to infinity. So what that means is that we are dividing the interval from a to b into n equal pieces. So we can find the width of each piece, and that's another symbol that we see in our sum, delta x. Okay, so the length of the interval is b minus n, by b minus a rather, but since we're chopping it into n equal pieces, we have to divide b minus a by n. So that is our delta x. And in this diagram here, we begin to see what this definite integral means. So here is a on the left, b on the right. So b minus a divided into 8 pieces in this diagram. We have 8 subrectangles. So each of these subrectangles has width delta x. Okay, so what about the height of this subrectangle? So that's where our function comes in. And we have this symbol xi star. All right, what does xi star mean? It's a representative. Okay, in each of the subintervals, okay, so we use delta x as like a measuring stick, right? Starting at a, we move to the right by delta x, and then by another delta x, and then another delta x, and so on. Okay, so those endpoints, we call them x sub 0, where the first endpoint is a, the left side of our integral. And then we have x1, x2 through xn. And that is, of course, our last endpoint, which will be on the right end of our interval. Okay, so within each of these subintervals, we are going to pick one representative point. Okay, there are lots of ways to do it. So in basic calculus, you saw, for example, the midpoint rule, the right endpoint rule, and the left endpoint rule. And fortunately, it doesn't matter which of those points you pick. You can even pick a random point, any point in between xi minus 1 and xi, the two consecutive endpoints. Okay, you can just randomly pick a point in there. Because we're taking a limit, it doesn't matter who these xi star are going to be. Pick whoever you like. So in this diagram, see how we are using the right endpoint. In our first subinterval, the height of the rectangle is the value of the function at the right endpoint. Okay, same over here, 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 6, 7, and 8. Okay, so we can approximate this definite integral by finding the heights of those rectangles using f of x, multiplying by delta x, so that will give you the area of a rectangle, and then adding them all together. Okay, now, why should we multiply all of them by delta x first before we add them all together? We don't have to, okay? Because this delta x is a constant which does not depend on the interval. It does not depend on I, okay? It doesn't matter which interval we're talking about, which subinterval we're talking about. Delta x is the same for each of these subintervals, okay? So in practice, if you want to approximate a definite integral using the right endpoint or any other method, all you have to do is add up the contributions of the f of xi star first, and then multiply the sum by delta x. Okay, so in other words, we can factor out the delta x from this Riemann sum. All right, so why should we get an approximation if we can find an exact answer? We always prefer exact answers in math anyway. Well, by now, you have seen many different kinds of integrals. And you know that sometimes it's possible to integrate a function. Sometimes it is impossible in the sense of using what are called elementary functions, polynomials, sine, cosine, e to the x, maybe a trig substitution. Okay, so maybe these memories from second semester calculus are making you a little bit nervous, but it's okay. We're going to review integration in a little bit, okay? But if you can find an antiderivative for your function, okay, so that's called capital f of x, okay? So that means that the derivative of capital f of x is small f of x, the original f of x, right? If you can find an antiderivative, yay, all you have to do is plug in the two endpoints, b first, followed by a, and subtract the antiderivative at a from the antiderivative at b. That will be the final answer, exact answer for your definite integral, okay? But again, that only works if you can find an antiderivative. Okay, so we also saw in basic calculus that, we also saw it in the diagram over here, that when you have a definite integral, the exact value represents the area of the region bounded by your function above, the interval from a to b below, and these two vertical walls, one at a and one at b. Okay, so this meaning will also be very similar to what we are going to see for double integrals. Okay, it will, instead of an area, a double integral will represent some kind of a volume. All right, and that makes sense because, well, area is in 2 dimensions, volume is in 3 dimensions. Okay, but I want to go over with you another way by which we can interpret a definite integral, and that is using the concept of a density function. Okay, so I have this diagram over here. There's no function that we can see in this picture. Okay, we have a thin wire from x equals a to x equals b. Okay, what are we going to do? Well, if this were a regular piece of wire from Home Depot, you can cut any piece of that wire anywhere along it. And as long as you're cutting the same length, let's say 1 centimeter from each part, you can't tell those pieces apart. Okay? You have a wire of uniform density. Okay? But what we have in this picture over here is a very, very special kind of wire. Okay? We don't see it. We have to use a little bit of our imagination. But if you cut a little piece of that wire with a width of delta x, now it matters where that piece of wire is from. Okay? If you cut a piece of wire over here, and then you put it on a little weighing scale, what you get as the mass of that wire will be different if you cut the same length over here on this side of the wire. Okay? So when something depends on a location or a coordinate, it becomes a function. All right? So that is what a density function is all about. Okay, so let me scoot up over here. Here we go. So the density at xi star is the limit as this width delta x right here goes to 0 positively. Okay, length has to stay positive. Of the mass of this wire, and this is basically representing the interval from xi star minus delta x over 2 to xi star plus delta x over 2. Okay? In plain English, this interval is the interval that we get at xi star, centered at xi star, of width delta x. That's why we have to divide by 2. Okay? So what is density? You need the mass of that little piece divided by the length. All right? And if you've taken chemistry or physics, you might say, wait a minute, shouldn't that be volume? Well, this is a linear density function, okay? Because our piece of wire is only in the shape of a line segment, we're assuming it has negligible thickness, negligible diameter, if it really were a piece of wire. And all we really need is that length, delta x, okay? So because of that, and you also have to do special consideration for the endpoints, okay? It's not a very big deal, okay? So what that means is we can solve for the mass of that piece of wire approximately as the density multiplied by delta x, okay? So you move the delta x over to the left side to join the density function. Okay, and then what do? We sum all of those little masses, their contributions, but hypothetically, theoretically, we want to take a limit as the number of these pieces go to infinity. That looks very familiar. That looks exactly like the definite integral that we just reviewed. Okay, so that now becomes the integral from a to b of our density function dx. So let's go to Scientific Notebook and let's actually compute some examples. All right, so let's introduce a problem over here. A piece of wire from x equals 1 to x equals 4 has density rho of x equals 1 over x. Find its exact mass. Okay, so what does this mean? What does this density mean? If you cut a little piece of wire, of this wire, the density will depend on where you cut it, and that density will be 1 over x, where you cut it. So if you cut it near x equals 1, just to the right of x equals 1, the density will be 1 over 1 or 1. But if you cut it near x equals 4, at the extreme right edge, to the left of x equals 4, that density will be 1 over 4. It's a lot lighter at that right endpoint. Okay? What about in between? If you cut it at x equals 2, the density will be 1/2. If you cut it at x equals 3, it will be 1/3. Let's go to GeoGebra and we can see a little better what I'm talking about. All right, here we are, and we're actually going to stay in just 2 dimensions for this. So first of all, we have a piece of wire from 1 to 4. Okay, so I'm going to use the line segment feature right here, and here we have boom, up to 4. Okay, there you go. So there's our piece of wire. We can actually see that piece of wire. Okay, now our density is 1 over x. We don't see the density. Okay, so just looking at this wire, we don't know how heavy it is over here or over here or over here. Okay, but we can graph the density in GeoGebra. Okay, so what did I say? If you cut the piece of wire over here, the density is 1. If you cut it over here, the density is 1/2. Over here, the density is 1/3. Over here, the density is 1/4. Okay, so if you cut a piece of wire all of the same width at those 4 points, all right, the density that you will get will be approximately 1, 1/2, 1/3, and 1/4. It won't be exact because to find the density, you need a limiting process, okay? And we cannot actually perform a limiting process physically because a limit involves infinity. And we don't do infinity in the physical world, okay? So let's go back to Scientific Notebook and we will find that total mass. All right, so the formula says that the mass is equal to the definite integral from a to b of the density, which is rho of x dx. Okay, so who are our a and our b? Our a is 1, starting point. B is 4, ending point. Our density is 1 over x. Let me just copy that over here. 1 over x dx. Okay, and if I were in the classroom, I would ask you all, does anyone remember an antiderivative for 1 over x? And I hope you don't disappoint me. That antiderivative is ln of x. Okay, so we are performing a definite integral. So remember in the notation, we need to put a bar over here on the right, and then the limits 1 to 4. Okay, so I'll just use this bar over here, and subscript 1, superscript 4. Okay, so that's how you would write it, and we plug in the endpoints. All right, so 4 goes first. We have ln of 4 minus ln of 1. And again, I'll ask you all, okay, do you remember what ln of 1 is? And that is simply 0. Okay, so our final answer is ln of 4. That is the exact mass of this wire. Okay, so if this wire actually existed, and you put this on the whole wire on a weighing scale, it will read ln of 4, which is approximately how much? Yeah, it's about 1.386, whatever unit we are using. Maybe it's in grams, maybe it's in something else. All right, so that was a fairly easy computation. Let's do something a little bit more sophisticated. A definite integral of sine of 3x dx, okay? So the technique, of course, is just a simple u substitution, okay? So we will use as our u, we have actually 2 choices. You can use just 3x, or you can use the whole thing, sine of 3x, okay? I think, though, that 3x will be the better choice, okay? So u will be 3x, and so du is 3 dx, okay? You take the differential, right? And then remember, you also have to replace dx in our integral, okay? And so we will have dx is 1/3 of du. Okay, so let me fraction here, 1/3 du. Okay, now you have two ways to do this, right? You can find an antiderivative for the function first and then plug in the endpoints, or you can also change the limits of your integral, change the endpoints, and then you don't have to go back to x. Okay, I will use the first one because when we do double integrals, we normally don't change our limits until we get to what's called the outer integral. Okay, so I will keep the limits at pi/6 and pi/4. Okay, so what have we got there? So first we will find an antiderivative for sine of 3x. Okay, so we will start with the indefinite integral. And based on our u substitution, we will have sine of 3x is now sine of u because our 3x is our u. Dx we have to replace with this. Okay, so we can just copy this over here. And of course, we can take the 1/3 out of the integral. We know our properties. And we are left with an antiderivative that everybody should know. So is the answer cosine of u or the negative of cosine of u? If this were a Zoom lecture, I will be taking a survey. So I hope you got it right. It should be negative. Negative 1/3 of the cosine of u. And if you don't believe me, you can check by taking a derivative. Okay, what is the derivative of cosine negative sine? Okay, so you will have the negative canceling with the other negative to give you positive 1/3 sine u. Okay, but we're not yet finished because we have to replace u with 3x. So there you go. There's our final antiderivative. Okay, so now we are ready to plug that into our definite integral. The definite integral is our antiderivative, where again we plug in the endpoints. So in the bar over here, at the bottom we have pi/6, and at the top we have pi/4. Okay, there we go. So what do we get? Okay, so the minuses are always dangerous, right? So we start with the upper endpoint, pi/4, cosine, so negative 1/3 cosine 3 pi/4, and we subtract. So the minus goes away. You know what? Let me put it in as a double minus. Okay, so we have a minus 1/3 cosine 3x, where we replace x with pi/6. Okay, there we go. And so let's simplify the second term, because again, we have a minus, so that should be delete, 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 plus 1/3. Okay, and we can of course simplify 3 pi/6 to just pi/2. Okay, so next, do you remember your trig? So cosine 3 pi/4, you're in the second quadrant. Okay, so the cosine is negative, and that should be negative radical 2/2. Okay, so we have minus 1/3. Copy this, and I also need for our cosine, we will have a negative radical 2/2. Okay, so let's make it look a little nicer. All right, so there you go. Negative radical 2 over 2. Okay, what about cosine pi over 2? You remember what cosine pi over 2 is? That's a 0. Okay, so that is going to be plus 0. So we have a nice answer. Our final answer is going to be radical 2 over 6, and it is a positive coefficient. Radical 2 over 6. Okay, did we get it right? I can ask Maple, and radical 2 over 6. Same answer. Let's go back to GeoGebra and see what this means. Okay, pi over 6 to pi over 4 sine of 3x. All right, so I've cleaned up our mess, and now we are going to input our function sine of 3x. All right, so there it is, but we are only going from, what did we say, pi over 6 to pi over 4. Okay, so we can put up vertical lines. X equals pi over 6. All right, so there it is. And x equals pi over 4. Ah, there it is. Okay, so it's a very narrow domain, okay, interval. So the answer that we got, which was square root of 2 over 6, right? That represents the area under sine of 3x between these two vertical walls, okay? And of course also bounded below by the x-axis. Okay? So that area should be around square root of 2 over 6. Okay, is that a reasonable answer? Yeah, that's only about maybe 0.3, and the height is almost 1. Okay, so let's go back and check that our answer is reasonable. All right, so what are you approximately? Oh, 0.23. Yeah, so that is a reasonable answer. All right, so for our final numerical example, we're going to review integration by parts. Ooh, vectors. Where did those come from? Okay, so remember the integration by parts formula. The antiderivative of u dv is u times v minus the antiderivative of v du. Okay, and if you have a definite integral, then you adjust by plugging in the endpoints for uv and plugging in the endpoints for that antiderivative. Make another definite integral. Okay, and you need to choose wisely what is your u, what is your v going to be. Okay, so and remember the point here being from dv you need to construct v, and from u you need to construct du. Okay, so you need to choose a dv which is easy to integrate. Okay, and also where this product is easy to integrate. Okay, so you have a little double whammy coming up. Okay? But if you remember, in this case, a good choice for the dv is the sine of 3x. Okay, so let's use dv will be sine of 3x dx. So the dx also has to be part of our computations, and our u will be x. Okay, so double check that everyone in this integral is in one of these equations. Okay, so x sine 3x dx, everybody's there. Okay, so I chose this example because we already integrated sine of 3x dx in our last example. Okay, we said that the antiderivative of sine of 3x dx is minus 1/3 cosine 3x. Okay, so we already have that. V is minus 1/3 cosine of 3x. All right, so what about u? If u is x, then du equals dx. Okay, so those are the equations that we need to perform the integration by parts. Okay, so let's copy this over here. So this will be the product of u with v. So let me just copy this over here and multiply by that x. Okay, so minus x over 3 cosine 3x. And we will plug in from 0 to pi over 3. And so the bar is really small. Later on, I will use something in scientific notebook that will adjust with the height of our notation here. Okay, and then we have to subtract v du. V is over here and du is over here. But since there's a minus here, it's going to end up as plus 1/3 cosine 3x integral. So let me copy that. Integral from 0 to pi over 3 of plus 1/3 cosine 3x. And you have a dx there. All right, so we will need another u substitution here, okay? But it's really the same. U will be 3x, so the antiderivative, and so du is 3dx, dx is 1/3 du, okay? And so when we get that antiderivative, okay, what's going to happen? Well, how about we perform the plugging in right now? So at pi over 3, you're going to get pi over 3 for x, and 3x times pi over 3, you're going to get pi. There you go, okay? Fortunately, when we plug in 0, it goes away because you have that extra x. So you're going to have a minus minus or plus 0. Okay, I'll just put it there for, even though it's redundant. Okay, and now we have this antiderivative. So we said that you have an extra 1/3 for your du. So that's going to be 1/9. Okay, and antiderivative of cosine, is it sine or negative sine? It should be a sine. It's a sine. There you go, sine of 3x. Again, quick check, okay? If that is the correct antiderivative, then if you take the derivative, you should get 1/3 cosine 3x, positive, okay? The derivative of sine is positive cosine. So you'll get cosine 3x, the 3 goes out by the chain rule, 3/9, you get 1/3, okay? And we plug in the endpoints as before, from 0 to pi over 3. Okay, there we go. And again, what are we going to get? So, oh, by the way, what is the cosine of pi? Is that 0? No, that is -1. Okay, so that term does not go away. You'll get negative pi over 9 and times -1. Times -1. Okay, and then you will plug in the endpoints over here. So at pi over 3, we are going to get sine of 3 pi over 3, that's pi. And what is sine of 0? That's another 0. Okay, but, oops, I'm sorry. There should be a plus over here. Wait a minute, that doesn't look right. Fortunately, what is sine of pi? That is 0. Okay, so, whoops, I also forgot. I said 9. I didn't write down the 9. Okay, so there we go. And so, of course, our final answer is simply pi over 9. Okay, so let's see. Are we correct? Oh, thank God. Yes, that is a pi over 9. All right. Phew. All right. Excellent. All right. I did the computation. Earlier, I forgot the answer. I usually do. All right, excellent. We are correct. Let's go back to our handout, and we're going to finish this off by introducing what's going to happen next time when we generalize the definite integral to create the double integral. All right, so this is what we're going to see next time, and many times in the near future. We're going to construct new kinds of integrals. So if you squint your eyes, they will all look like this, right? You'll have an integral sign, and then you'll have a domain, which we will write maybe as capital D or capital R or capital S or some other symbol. And sometimes there will be two integral signs or three integral signs, okay? It might be a double integral or a triple integral. You will have a function, and you will have something inside that function because we have to evaluate that function somewhere, okay? So we just finished our handout on thinking in 3 dimensions, where we talked about functions in 2 variables, okay? So when we do the double integral, you'll have a point here with both x and y, okay? So that is what capital A represents. And then you'll have a differential here, dq. Okay, so depending on what flavor of integral you have, that might be a dA or a dV or a ds, lower s, or a d capital S. Okay, and there might even be an arrow on top. Ooh, vector. Yes, there will be vector integrals, something to look forward to. Okay, what does that dq represent? It represents a measure on the domain. Okay, so what does all of this mean? Let me scoot out of the way here. There we go. Okay, so remember the definite integral. Okay, it was limit as n goes to infinity, summation I equals 1 to n, f of xi star delta x. Okay, so we started out by subdividing AB into small pieces. Okay, so in the same way, we are going to subdivide the domain of our function, capital D, into small pieces, okay? So we're going to start with the rectangle next time, and we're going to cut up that rectangle into small subrectangles, okay? We will measure the size of each little piece, okay? How big is one of these tiny subrectangles? Within each subpiece, we are going to pick a representative point. Where will we plug in? What will we plug into our function? Okay? Then what are we going to do? We will form a Riemann sum. We will take the value of that function at the representative point, multiply it by the size of each little piece, and then we're going to add it all up. Okay? But the hard part that, again, we won't see in reality is to take the limit of that Riemann sum. Okay? What's going to happen as the number of pieces goes to infinity? Right? So that is the last step in the process. And the number that we get, hopefully, is going to be the value of our new kind of integral. Okay? Now, we have the fundamental theorem of calculus that says, okay, all you have to do is find this antiderivative, plug in the endpoints, what we just did a few minutes ago. So in the same way, we're going to see theorems that will help us to actually compute these new integrals exactly. Okay? And for the first couple of theorems, those are called Fubini's theorem, variations of the fundamental theorem of calculus. All right, so I'm going to end right there, just under 40 minutes. So when we come back next time, we're actually going to dive in to the definite double integral, and we're going to do some calculations. All right, so until then, I will see you next time, and enjoy the rest of your day. Bye.